All right, for 2.6, we've got limits at infinity, which is really just horizontal asymptotes, something you know from pre-calc, which we'll refresh in the beginning, and then we'll kind of verify things with calc, sort of like we did with the continuity. So in college algebra, pre-calc, we had 3 rules for horizontal asymptotes of rational functions. The numerator and denominator had the same degree. Then the horizontal asymptote was the quotient of the leading coefficients. So if we had a function f of x that was like a sub x to the n plus some more lower powered things, and then some bx to the n plus some lower powered things, our horizontal asymptote was y equals a over b, right? The quotient of those leading coefficients. If the denominator had a larger degree, or higher degree, meant our horizontal asymptote was just y equals 0. And if the numerator had a larger degree than the denominator, we didn't have a horizontal asymptote. Right, those are the cases you looked at maybe where the power was 1 bigger, and then we had the slant or oblique asymptote, which was just a line of the form y equals mx plus b, right? So we actually had a slope that wasn't 0, right? It's not just a horizontal line. And then if the degree is like 2 higher, you could have a parabolic asymptote, things like that. But you really only looked at degrees that differed by 1. So if we're looking at the first problem here, both are degree 2, right? Both have x squared. So our horizontal asymptote is just y equals 3 over 1, or 3, right? The quotient of those leading coefficients, because we'd have a 1 in front of the x squared. Formally, definitions of limits at infinity. If L is a real number, the statement, the limit as x approaches infinity of f of x equals L, means that for each epsilon greater than 0, there exists an m greater than 0 such that the absolute value of f of x minus L is less than epsilon whenever x is greater than m. All right, and really, epsilon is just a tiny number. I'd say positive, but the greater than 0 is already there. So it's just some really small value. And it says if we go out far enough past some value m, then we're going to stay within this teeny tiny amount of L. So it might wiggle along or cross it, but we're going to stay really, really close. And same thing for the second part, going out to the left. As we go past some value n, we're going to stay really close to this limit. And we can draw a little bit on a picture below, but we're not going to do a lot with the formal definition, so it's just this idea of closeness again that we've talked about for the height of the function. Our definition for the horizontal asymptote, the line y equals L is a horizontal asymptote of the graph of f if the limit as x approaches infinity or minus infinity of f of x is equal to L. And so here's our little picture of the one we found the horizontal asymptote for above, the one at 3. And so it's just saying if we go far enough out, really in either direction for this one, but this won't be bigger than 3 plus epsilon or 3 minus epsilon. So our value is going to stay within that little epsilon window or range around 3. And the epsilon doesn't matter. You're supposed to be able to prove it for any tiny number. But the idea, again, is just that closeness. We stay really close to this height, and that's why it's the limit. So you can see it from the picture, our limit going towards infinity or minus infinity, both of those are 3. And for the rational functions, we're always going to have the same horizontal asymptote whether we go left or right. When you bring in the transcendental functions, the ones that can't be written out or combined algebraically, so like sine and e to the x and some of those things, you could have 2 different asymptotes. And we'll look at that with the next problem. So we want to show this one has 2 different horizontal asymptotes. And to do that, we really just need the graph of e to the x, so we can think about which direction we're going. So we've got our nice exponential function going through 0, 1, and we can see what happens as we approach infinity or minus infinity now, right? This being our, again, y equals e to the x. So the 2 and the minus 1 aren't really going to do anything, so we're just kind of thinking about what happens with the e to the x function as we approach negative infinity for the first part or infinity for the second. And you can see as we approach negative infinity, right, as we're moving out to the left here, we're getting really, really close to a height, or we have a limit of 0. So as we evaluate this one, the constants stay the same, but we get a 0 for e to the x as x approaches negative infinity, which gives us a -2 for our limit. As e to the x goes off towards infinity, right, moving to the right, it's getting really, really big, so we're going off towards infinity. -1 is not going to change the fact that it's a 2 divided by a really, really big number, so this is just going off towards 0. And if it helps to write out the infinity and see it, that's fine, but it's basically 2 over infinity, so it's going to 0. All right, and if you wanted to think about, I guess, the little limits we used up there, so our limit as x approaches minus infinity of e to the x was 0. Right, we can see it on the graph, and then our limit as x approaches infinity for e to the x is infinity. And again, knowing those base graphs will help. You might have e to the minus x in a problem, and drawing that out and kind of seeing where it goes will help you. So this theorem is what I was kind of using in that last problem, but it's also kind of common sense. If we have a constant value, it doesn't matter if it's 1, they're just kind of using that property where we could pull a constant out front, right? And it's still going to be like c times 0, so it's still 0. But any constant divided by one of these power functions, x to the r, where r is a rational number greater than 0, otherwise, right, it would come to the numerator. But anytime we have a constant divided by this big value, the whole thing's going to approach 0. So think like 1 divided by 1, 1 divided by 10, 1 divided by 1,000, 1 divided by 1,000,000. That number's going to get smaller and smaller and smaller as your denominator gets bigger. And it doesn't matter if we're approaching positive or negative infinity, it's still a constant divided by a giant number, so that whole fractional value is approaching 0. So we're going to use that kind of throughout this section to algebraically solve for the limits here, and to kind of see where those rules we had in pre-calc come from, right? Why the horizontal asymptote is what it is. So we can write out with the limit properties. You don't, again, have to do this. I'll probably do it for just the first one so you can kind of see. But again, we're back to those limit laws from 2.3, right? The constant can get out. We've got a 1 over x cubed, and then our limit as x approaches infinity for 7 as well. So we just got from the above, theorem 5 here, that limit as x approaches infinity of 1 over x cubed is going to be 0. Right, that constant outside, we can write a 3 times 0 plus 7, or our whole limit here is just going to be that constant 7, because that first term is going to go to 0 as x gets really, really big. So same thing then for the other parts. We looked at e to the x above. You could always do another quick sketch if you don't remember. But as we go towards negative infinity, e to the x approaches 0, and the constant stays, right? For whatever value of x we're approaching, right? It's got a constant height again of 2, so we're stuck there. And 0 minus 2 gives us -2. For c, the second and third terms are fitting that form you can see above in the theorem. So as x approaches minus infinity, those two terms are both going to approach 0. So we end up with just that constant 7 as our limit. And for the last one, we've still got e to the x over here. We can see that as x approaches infinity, e to the x approaches infinity still. If you wanted to rewrite it with a 3 times 1 over e to the x, you can still see again it's that 1 or that constant divided by a giant value. So this whole thing is just going off to 0. Right, so 3 divided by an increasingly bigger and bigger and bigger number is getting smaller and smaller and smaller, essentially approaching 0. Right, so it's kind of what we're using throughout this whole section. We do have another indeterminate form, If the numerator and denominator both have a limit of infinity, we get an indeterminate form, infinity over infinity. Doesn't matter if it's positive or negative, but just some form of infinity over infinity. We divide each term by the highest power of x in the denominator to evaluate the limit. And really that's just to keep from zeroing out the denominator, right? We still don't want to divide by 0, so we're going to use the highest power that appears there. So that highest power of x in the denominator is the important bit. And I'll show you as we do them. So you know again from the pre-calc that our horizontal asymptote here will be 0, right? We've got degree 1 in the numerator for 5a, degree 2 in the denominator, so the denominator is going to grow bigger. But if you just tried to evaluate the limits with those limit laws, you'd get infinity over infinity, because we just have a giant positive number in the numerator and a giant positive number in the denominator, right? If you want to see more work than you need, if we're kind of think if we just throw in infinity, right, it's not a number, but it just represents a giant positive value, right? There's nothing we're doing here that's going to get rid of anything. So like 2 times infinity plus 5, I don't know why I got an extra parenthesis here, but that whole thing is just a giant value, so infinity. And infinity squared times 3 plus 1 is still some big positive value, so both are going towards infinity. So in order to evaluate and see where those rules from pre-calc come from, we've got to rewrite that limit, and we're going to divide every term by that power of x, highest power of x in the denominator. All right, our highest power of x in the denominator is the squared, so we're dividing every single term by x squared. And even though we phrase it as dividing every term by x squared, or the highest power, you're essentially just multiplying both pieces of your fraction, right, numerator and denominator, by 1 over x squared. So we are just multiplying by 1 in the form of what we need. Same as you've done working with fractions or rational functions your whole life. We're just kind of taking care of that distribution all in one step, right? As we did multiply this in, we'd get the 2x over x squared plus the 5 over x squared. In the denominator, the 3x squared over x squared plus 1 over x squared. So if we just divide every term by that value, we're taking care of that distribution in one step. And then you just need to simplify and invoke that theorem from above. So we get a 2 over x, 5 over x squared doesn't simplify at all, just a 3, and 1 over x squared. And so we're using this property again, this constant divided by x to some power as we go towards positive or negative infinity, to zero out 3 of those 4 terms. So this 2 over x, 5 over x squared, and 1 over x squared are all going to 0. Which is just going to leave us, as we take the limit, with a 0 plus 0 over 3 plus 0, or 0. All right, and again, it kind of confirms what we had from pre-calc, where bigger degree in the denominator, horizontal asymptotes y equals 0. Right? And if that horizontal asymptotes y equals 0, then our limit as we approach positive or negative infinity is also 0 for the rationals. Again, for those transcendentals, we could have different values on both sides. But again, looking at B, you should know the answer. I won't say this one, I guess, but it's there for you. And we'll just confirm with the calc. So we've got powers of x to the first in both. If you wanted to look at what happens just with that direct substitution, just to kind of think about what the values represent again. We've got a 3 minus 5 times infinity. So it's a 3 and then a big negative value, so that'd be a negative infinity. 3 times a positive giant number minus 1 is going to stay positive and giant, so we're going off towards infinity. So we've got that infinity over infinity form. Again, the sign doesn't matter. And we'll break it down the same way we did the first one, where we were going to divide by the highest power of x in the denominator. This time we just have an x to the first there. So we're going to divide every term just by x. All right, and then when we simplify, got a limit as x approaches infinity of 3 over x minus 5 over 3 minus 1 over x. And so those two values with the constant over x, as x approaches infinity, right, the denominator's getting huge, so the whole fraction's going towards 0. And we're left then with a negative 5 over 3, which, if you were paying attention earlier, remember your pre-calc, right, is the quotient of those leading coefficients, right, the negative 5 over 3 there. We had x to the first, or first degree for both, so a over b gives us that horizontal asymptote, or that limit as we approach infinity. All right, for c, we can still see, maybe hopefully without plugging in a quadratic function, a linear function, both are going off towards infinity as we approach negative infinity, or going off towards negative infinity, but we're still getting that indeterminate form. And if you want to plug it in, you still can, but a little harder to see what's happening with the 2x squared minus 4x if you're plugging in big numbers there. So just thinking that they're both giant and we want to divide by that highest power of x in order to simplify and find this limit. I started writing, but we need to keep that limit until we evaluate. So limit as x approaches minus infinity. We've got a 2x squared minus 4x. And denominator, the x plus 1, and we're going to divide each term again by the highest power of x in the denominator. That's x to the first. So dividing all four terms by x, and we can see what happens. We're going to simplify first. Limit as x approaches negative infinity of 2x minus 4 over 1 plus 1 over x. All right, and as we substitute in here, the 1 over x is going to go to 0, and since we're subbing in a negative infinity, the 2 times some big negative number is still negative, minus 4 still negative, so this whole limit should go towards a negative infinity. All right, and you can write it out again. I could fill it in. Just so you kind of see again, it's that positive 2 times a big negative number, minus 4. Still going to be negative, divided by 1, or 1 plus 0 if you want to write them both. Is still going to keep us with this big negative number. So we're approaching negative infinity. And if you did want to do long division, you could find the equation of that slant asymptote if you had to graph. All right, D is a little different in that we've got a square root involved. So dividing by that power of x is going to look slightly different. But we still got this infinity over infinity if we substitute our infinity in for x, or substitute a giant value in for x. So we're going to divide by that highest power of x in the denominator. All right, and that's all we really have to work with right now. So our limit as x approaches infinity of our square root of x squared minus 1 over 2x minus 1. We're going to divide every term by x. You can see I just did the whole denominator by x first, so we look at how it actually goes into that square root. And so the piece you need is that x, well, we're approaching this nice positive infinity, is the same as the square root of x squared, right? And you remember, and hopefully from algebra as we write that out, that if we've got the square root of like a to the n over, I don't need an n there, let's just do square root of a over b or something, right? This is equal to the square root of a over the square root of b. But we can only combine those if we've got the same index. So like if it was square root of a and cube root of b, we wouldn't be able to put them together. So the fact that we've got that square root in the numerator means we have to view x in some form as a square root to bring them together and actually divide those terms by our x power that we grabbed from the denominator. So underneath this radical, I can write it as an x squared minus 1 over x squared for both, right? And that's again me taking this x as a square root of x squared, right? And then being able to combine those radical functions since I've got the same index for both. All right, and then my denominator, we can do all the reduction together. So 2x over x minus 1 over x. When we reduce them, we've got our limit as x approaches infinity. Under the square root now, we've got a 1 minus 1 over x squared. Our denominator, we've got a 2 minus 1 over x. Remember that limit can go inside the square root. We're still just going term by term. We end up with the square root of 1 over 2 as the 1 over x squared and 1 over x go to 0, which is just 1/2. All right, one more slightly weird one here. It's a technique we practiced in a couple other sections, and I figured good to do again. So if you did plug in infinity here, which we've kind of skipped for a couple of the ones right above, but you get this infinity minus infinity, and we don't know which infinity is bigger, so we have no idea what happens. So it's maybe an indeterminate form we'll talk about in a later section, but if we do get something like this, we can still, since we've got that radical, multiply by the conjugate to solve. So we've got a limit as x approaches infinity of x minus the square root of x squared plus x. We need to think of it as a fraction because we can't just multiply by a value unless we do it in the numerator and denominator. So my radical, or my conjugate, is an x plus that square root x squared plus x. I've got to do that in the numerator and denominator, so I multiply by 1 to change the way it looks without changing the value. And by what we know about conjugates, that's going to make my numerator an x squared minus the quantity x squared plus x, right? That value that comes out underneath the radicand when we square it. And then in my denominator, I've got that whole is just a 1 times, so the whole x plus the square root of x squared plus x stays there. All right, and as we work through then, we can distribute, end up with the limit as x approaches infinity of minus x over x plus the square root of x squared plus x. And now we can divide by that highest power of x in the denominator to finish it off and find our limit. So equals the limit as x approaches infinity of minus x over, I guess there's one more thing I could mention, but we're going to divide by x. I'll do it in a sec. And then the x plus square root x squared plus x. Again, to take this power, this x inside the square root, we need to turn it into that square root of x squared. So both terms inside are getting divided by x squared. And the reason we can go there, I should at least mention it, if not write it out. If you did plug in the infinity and try to solve here, you'd get a negative infinity over infinity. Right now that we're doing addition in the denominator, it's just big number plus big number, so it'll stay as a big number. So we get that indeterminate form, and then we can continue with the dividing by the highest power of x in the denominator to simplify. All right, and when we do simplify this, we've got our limit as x approaches infinity of negative 1 over a 1 plus under our square root, 1 plus 1 over x. As x goes to infinity, that 1 over x is going to disappear, right? It'll go towards 0. And we're left with a negative 1 over 1 plus the square root of 1, or a negative 1 over 2. All right, so probably the hardest one, but practicing the multiplying by the conjugate again, rationalizing the numerator as it were here is always good. All right, and the rest is just a little bit of graphing, kind of refreshing some more maybe we know from pre-calc. But polynomial functions won't have horizontal asymptotes, but we can use the idea of infinite limits at infinity to understand the end behavior of the graphs. So if I do draw up x cubed and x to the fourth here, and you could use x squared exactly the same way as the x to the fourth. Right, you learned about end behaviors for even and odd degreed functions, or degreed polynomials at least, in pre-calc. And so x cubed here, you can see as we go towards negative infinity for x, we're going down towards negative infinity for y. All right, as we go off towards positive infinity, we're going off towards positive infinity for the y. All right, and then for the x to the fourth, or the even powered ones, right, x squared, x to the sixth would all look about the same. As we go off towards negative infinity, we're increasing to positive infinity. And as we go towards positive infinity, we're still going up to infinity. All right, so we can look at those limits. And then for the x squared minus x, if you try direct substitution, we can't see what's happening again. It's just big minus big. So don't know. But if we look at it in a factored form, we've got an x times x minus 1. If I plug in infinity there, I've got infinity times infinity essentially, right? Because infinity minus 1 is still basically infinity. And we're just multiplying two big giant numbers together, so it's still a big giant number. All right, but those limits at infinity for our polynomials, keep those in mind. They'll help us when we get to the graphing later on. All right, so using the graph just to evaluate some limits. I don't say it enough because I don't want to just keep repeating, but pause, try it, check your answers if you need. But f of 0 would be -1. Limit as x approaches negative infinity. We can see going out running along -2, right? So 0, f of 0 is right here. We're taking the filled dot, right, not the whole. And then as we're approaching negative infinity, we can see we're sticking at that height -2. As we approach positive infinity, maybe it's meant to stop somewhere slightly above, but I would say that's definitely approaching 0. Our limit of f of x as we approach 2 from the right. So coming in along this piece of the function, right? 2 from the right, we're going up towards infinity. As we approach 2 from the left, coming down along this piece, going off towards negative infinity. And f of 2 itself is undefined or does not exist. I feel like we usually use undefined for points and does not exist for limits and things, but at least the function's undefined at 2, so f of 2 does not exist. So whatever you write's good there. But just trying to read the graph a little bit. And then we want to kind of take that same thing, flip it on its head, and try and draw a graph based on information given. So we can go off the limits and try and draw in asymptotes. We can mark points, any points we're given, and then we'll just try to draw the function in towards those limits, those asymptotes we draw in and know. So the limit as x approaches 2 is infinity, which would hopefully mean, oh no, positive 2, okay. So for positive 2, I saw the -2 below it and got scared, but no. Positive 2, both pieces are going to be going up towards infinity. Right? If the limit as x approaches 2 of f of x is infinity, then we've got to be going off towards infinity on both sides. For the -2, we can see for the left side, I'm looking at the second one, but okay, if I go in the order that they're written, as we approach -2 from the right, we're going off towards infinity. And as we approach -2 from the left, we're going down towards negative infinity. All right, for the function f of x, the limit as we approach negative infinity or positive infinity is 0, so that gives us that horizontal asymptote at 0. And then f of 0 is 0, so we've got a point in there. And then you're just kind of piecing things together. So we don't know if approaching 0 as we go towards negative infinity is coming from the top or the bottom, but if we piece it up with the other thing we know, that the limit as we approach -2 from the left is negative infinity, we can get a piece of our function in here that fits both, right, of those limits given. For the middle of the function, we're going up towards both of those asymptotes, and we've got a point at 0, 0. So we can just draw a little parabolic piece up from there towards the limits. Right, if we did go down at all, we'd have to have other x-intercepts in there that we'd come back from. And you know what? You could probably try and draw another function that would fit all these criteria, but usually the easiest one, or the most basic one, is the easiest. And then same thing going out towards positive infinity. We don't know if it's above or below, but easiest option, since we've also got to approach infinity as we come at 2 from the right, is to fit a piece in up there. All right, So it's good practice. Hopefully there's some in the book like that still. Otherwise we'll do some together. But if you can go both directions with it, that's good. Again, what we're kind of seeing from these limits, if we're kind of attaching it or connecting it to the graph or the pre-calc, we've got vertical asymptotes at x equals plus and minus 2, because we've got at least one limit going towards infinity as we approach. And then we've got our horizontal asymptote here at y equals 0, right? Because we're approaching 0 as we go towards infinity or minus infinity. And then we were just given 1 point, which would be our x or y intercept. So if it's a graph, probably a graph you could figure out the equation for from pre-calc, but for now we just want to graph it, given those limit rules. Maybe we'll practice some more, but that's it for 2.6. Hopefully not too bad. I'll see you in 2.7.